What you're looking at right now is basically the scientific version of voodoo. Yeah, like actual African black magic. But in physics, this thing actually has a name. It's called quantum entanglement, a phenomenon so weird that even Albert Einstein himself called it spooky action at a distance.
Spooky action at a distance.
That's spooky action at a distance.
What you do over here having an effect on something over there.
That it doesn't even matter how far apart these objects are in space, they're just connected.
Yeah, this phenomenon shows that we can affect something from insanely far away, to the point where the idea of distance itself almost feels like it doesn't exist anymore. Sounds crazy, right? And that's exactly how the quantum world works.
What does that mean?
It means that you would enter a reality where all concepts of time and space become irrelevant.
This is the essence of the weirdness, of the spookiness in the quantum world.
So, what exactly is quantum entanglement? And why did Einstein call it spooky? Let's talk about it. Alright guys, this is a continuation of our discussion about the quantum world. Now if you're new here, the quantum world is basically the subatomic world, the world that exists inside an atom. In the previous video, we talked about some really weird phenomena, things like superposition and the observer effect, a condition where a particle can exist in multiple places at the same time, and somehow it can know whether it's being observed or not. And because of these bizarre phenomena, it eventually led to a debate between Albert Einstein and his own colleague, Niels Bohr. Because at the 5th Solvay conference, in front of some of the greatest scientists in the world, Niels Bohr made a bold claim. He basically said, quantum theory is already complete, which means we just have to accept it, that at the quantum level, reality is just random and can't be predicted with certainty. But Einstein didn't agree with that at all. For him, we can't just accept something this weird without a real explanation. Like, how does physics, something that is built on precision, suddenly turn into something random and unpredictable?
Laws of nature were no longer definite statements about what's going to happen next. They were just statements about probabilities. And Einstein felt, well, that's defeat. You're giving up on the heart of what physics has been. Namely, to give a complete description of reality.
And because of that frustration, Albert Einstein, along with two other scientists, Boris Podolsky and Nathan Rosen, published this paper. When this paper came out, even the New York Times covered it with the headline, "Einstein Attacks Quantum Theory." Basically, in that paper, Einstein was trying to show that quantum theory wasn't complete. He believed something was missing. For Einstein, reality should be clear, not just a bunch of random probabilities. So to prove that quantum theory was incomplete, Einstein came up with a scenario that we know as Ep.3 paradox, a thought experiment that ended up leading to something even stranger, a phenomenon that pulls us deeper into the weirdness of the quantum world. That phenomenon is called quantum entanglement. So, what exactly is quantum entanglement?
The most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Now imagine this. You have two coins, and you flip both of them at the same time. Normally, when they land, the results are random, right? Sometimes they match, but sometimes they don't. Then imagine this. What if every single time those coins land, they're always perfectly in sync? If one lands heads, the other one is always tails. Or if one lands tails, the other one is always heads. And this keeps happening every single time. Or think of it like two dice. You roll them randomly, but somehow, every time they stop, they always show the same number. Yeah, both the coins and the dice start acting like they're connected, like they know what the other one is doing. And that's basically the idea of entanglement that Albert Einstein was pointing at in the Ep.3 paradox. According to Einstein, if quantum theory is incomplete, then it would lead to a situation where two particles can be connected to each other, just like the coins and dice we discussed earlier. Now imagine an even crazier scenario. What if we take those same coins or dice and separate them? not just on different tables, but on different planets. One on Earth and the other, let's say on Mars, or maybe even across different galaxies. Now, when they're separated by that kind of distance, what do you think would happen? Would the entanglement just disappear? Logically, it should be impossible for the entanglement to still happen, right? But the quantum world isn't that simple, because no matter how far you separate them, that entanglement still holds. Every time you measure one, the other one will instantly adjust. No signal, no delay. It's almost like distance doesn't even exist at all. Like space itself is just an illusion at the quantum level.
It's as if the two coins are secretly communicating instantaneously across space and time, even if the first coin was on Earth and the other was on Pluto.
And at first glance, this instant connection makes it seem like something is moving faster than light. And that's exactly what made Albert Einstein uncomfortable. Because how is it even possible for information to travel faster than light? That should be impossible. It literally breaks his own theory of relativity. But maybe there's something Einstein was missing. Maybe there's actually no signal being sent at all. Because what if those two objects were never really separate to begin with?
This suggests that the world is not made of separate elements. The world is one whole, all these things connected together over very long distances into a whole which is not analyzable into parts.
But whatever the cause, the point is, this was the paradox Einstein was trying to show to Niels Bohr. That reality couldn't possibly work like this. There's no way something in this universe is moving faster than light. There's no way two objects can communicate instantly like space and time don't even exist. And that's why Einstein called it spooky action at a distance. Something that just felt too strange to be real.
Because spooky action at a distance shouldn't be allowed in physics, Einstein had showed that it is impossible for any signal, any information, to be transmitted faster than light. And so you can't have this instantaneous action at a distance. There has to be some time for a signal to span the distance.
Back then, entanglement was still just an idea, something living inside Einstein's paper, and no one actually knew if this phenomenon was real or not. Then until 1964, when a physicist named John Bell came in with something groundbreaking. In his paper, he showed that this spooky idea could actually be tested. That idea later became known as Bell's theorem. So scientists started testing it. In these experiments, they fired lasers at a material, creating two particles called photons that interacted with each other. Then they separated them, sending one to the left and the other to the right. And each path had its own filter. Then, what happened? Entanglement actually showed up. Those two photons really did interact. They would either both pass through the filter or both get blocked. And when the test was repeated over and over again, and the results remained the same, they changed the setup, adjusted the filters, made the paths more complicated. The results remained the same. Even the directions they took matched perfectly. And yeah, these experiments showed that quantum entanglement is real. That two particles can actually affect each other instantly, even from really far away. And it didn't stop there. NASA even tested this in space. One particle on Earth, the other on the space station. And the result? Still the same. The two particles stayed perfectly connected, instantly affecting each other, like distance never even existed between them. And this is the moment when quantum entanglement was first captured. A point that finally confirmed what Albert Einstein once called spooky action at a distance is actually real.
By 1980, certainly by today, we know that entanglement is real. So this crazy feature of quantum mechanics that he tried to use against the theory itself is actually borne out by data today.
So that I'm obliged to admit that the quantum correlations exist in the world, and if we are to explain them and not just accept them as given, if we are to explain them, we are obliged to invoke something like actions going faster than light from one place to another.
But hold on, does this mean we can actually use this like some kind of black magic? Can we really affect someone from far away like voodoo? Well, probably not. That's a bit of a stretch. But what's clear is, quantum entanglement opens the door to technologies we never even imagined before. Things like quantum computers, which directly rely on this phenomenon. Even ideas like a quantum internet or data teleportation that are still being developed, all built on the same principle. But maybe the most interesting part of all this isn't the technology. It's what this phenomenon says about reality itself. Because if just two particles can stay connected, no matter the distance, then what about us? Are all the things we see in this world really separate from each other? Or maybe everything has always been connected as part of the same system? Because in the quantum world, we've already seen that a single system can exist in multiple possibilities at the same time. But once we observe it, all those possibilities collapse, leaving just one reality. But what if those possibilities never actually collapse? What if all of those possibilities actually happen? Just not in this world, but in other worlds that exist right next to ours. And that's the idea behind a theory called the many worlds interpretation. Or in Marvel, they call it the multiverse. In the next video, we're going to dive into that idea. Where do all those possibilities actually go? Do they just disappear, leaving only one outcome? Or do they all continue to exist somewhere else? We'll answer those questions in the next video. For now, the one thing you need to take away is, maybe we're all connected, as part of the same system.